Hello, everyone, and welcome to another episode of Alexa and Friends. My name is Jeff Blankenburg, and today I have Jasha Droppo, who is a senior scientist on the Alexa AI team. Jasha, thank you so much for being here today.
It's my pleasure, Jeff.
So one of the things that I like to do when we start these interviews is ask a couple of what I've referred to as silly questions. And I have not prepared you for these. You didn't know these were on the list of things we might talk about today. But the first one that I like to ask people about is related to superpowers and superheroes. Oftentimes, we've seen many movies over the past 10 or 12 years about superheroes and all the cool things superpowers that they have. And I'm always interested to know from our guests what you would pick. If you could pick a superpower for yourself amongst all the ones you've ever seen in comic books or movies, what is something that appeals to you as a superpower?
That is a fantastic question. There's all these superhero movies are the thing now. It seems like we go through cycles of, zombies being big, and then vampires, and then superheroes. Maybe we're due for another zombie apocalypse in the theaters. I always, I'm going to go with the classic here, Superman, because Superman can fly. It started out as leaping, then he's flying, and then he can do stuff with his eyes, and it's really the superhero that's been around for a long time, and his powers seem to really grow over time.
Yeah,
and so it's really hard to pigeonhole it. And the thing I really love about Superman is he can protect himself, and he's very strong. So all the tension in his stories come from threats to the people that he loves, the people around him, and the earth and the planet. And how does he reconcile being so all powerful but then still being vulnerable? And so that resonates with me. My son's gonna be upset with me because he is not a fan of DC comics.
No, he's a Marvel guy.
He's a Marvel guy through and through.
That's right. So what I generally do here, though, is I pin people down. We can live in the Superman world if you want to, but if you can only pick one of his powers or one of anyone's powers, rather than being the superhero themselves, you only get to pick one power.
For your power.
That's harder.
That is harder. I don't know. Super speed would be really fun.
I think so too. That's what I go for. That's something that comes up quite often, I think, because people always feel strapped for time.
Yeah.
But it's almost a sort of time travel in the way that it's portrayed in movies, right? They can slow things down so much that they're able to take advantage of turning a second into a minute or an hour.
That's right. Well, that's more of a Flash power, actually, I think.
Yeah.
But Superman and the Flash, I guess they fought in some of the DC products. But time travel does come into it. In the original Superman, the motion picture with Christopher Reeve, he does kind of, I guess, rewind the planet. That was a bit.
I don't think that's how the rotation of the Earth works, but he did it.
Yeah. Super speed is fun.
All right, so thank you for that. The second one is super fast, but it's a question that we probably will never get rid of on this show because people seem to enjoy it. So I want you to imagine for a moment you're walking through a large city, big city blocks, big buildings everywhere, and you need to get one street over. You're on 17th Street. You need to get to 18th Street. And you can see that there's an alley that'll give you easy access to make that walk from the street you're on to the street you need to get to without walking all the way around that big city block. It's safe. It's daylight. There's no reason to think that this is an unsafe alley. So you decide to head down that alley towards the place that you're going. And as you get about halfway there, you notice at the end that you're heading towards emerges a giant horse-sized duck. Big duck. At the other end, as you turn around to retreat from this perceived threat, you find 100 duck-sized horses. Very, very small horses.
Yeah.
My question for you and for everybody that's been on the show is, which direction would you go, knowing that you now need to find your way out of this alley? What do you feel is the end you will have the most success at exiting?
Right. So lucky for me, I've been on the internet long enough that I have encountered this question, this paradox or dilemma before, and I've given it some thought. And what you have to do is you have to go to the core nature of the animal. And horses are just like big puppies, right? People keep them as pets. They pet them. They're nice. Sometimes they make questionable decisions, but overall, they're big mammals, and they look like they act like puppies. Ducks, however, are mean SOBs, and not known for their great demeanor. If you had said a duckling, maybe, but a duck, a horse-sized duck, is not for me. I'm going to the end with the 100 puppy-sized horses.
All right. That is some solid reasoning. I've heard many definitions about how people would choose to go one way or the other. Yours is well thought out. I like that.
Thank you.
All right, so let's skip beyond the silly, because I really want to get to know you and kind of your history and some of the things that you're working on. So one of the things that we generally start the interview with, once we've gotten past that previous nonsense, is your background. Where did you come from? Where did you go to school? What were the decisions you made along the way? What does your career path look like? I'd love to hear that, that 5 or 7 minute story about where you went and what kind of projects you were interested in, and kind of how you landed where you are today.
Yeah, I owe a lot of where I am today to kind of the whole computer culture in the 70s and 80s, and the fact that my parents were involved in it. I mean, my dad, some of my earliest memories are him building wire wrap computers in his study. Wow. And going to the Hanford surplus sales and getting things like teletypes. If you've never heard of a teletype, it's like a typewriter, but it's the size of a jukebox, and it sounds like a freight train when it's going. And so before CRTs, this is the way you'd communicate with the computer: is it'd be hacking away and typing and shaking, and so that was great fun. And he would Mad Libs this Mad Lib program was one of my earliest memories. He would show me how to write a basic program, and you say prompt, like input a verb, input a word, input a adjective, and then it would fill it in and write out a little story. And so by the time I was 4 or 5 years old, I was able to modify the code and put in different Mad Libs. And so he got me started on the programming. I was also really fascinated with the intersection of what computers and audio could do as I grew up. I also want to mention the other person who really got me into computing was my mother, who was a teacher at the time, and she was taking classes on something called Logo, which is kind of a cross between programming and graphics. And John Crawford, who 12 years later would become my calculus teacher, taught her Logo, but I was sitting next to her, so then I would help her with her homework. So programming came in early. And then I got interested in the intersection with computers and audio. I did things like a grade school project on text-to-speech synthesis chip, where you could set little dip switches to a binary number representing one of the words it could say. And because the chip was from a clock, all it could say is like numbers and AM and PM, but it was pretty fun. It built like an electronic drum kit. And then later in middle school, I got this book from the University of Washington called Musical Applications of Microprocessors, which was just fascinating to me.
Yeah.
And I got into like sampling music on my Apple II, built a little circuit and modified it and played it back. And it was just great fun. So when I went to college at Gonzaga, I ended up studying electrical engineering because that was the closest thing to, what I wanted to do. This was just before Gonzaga. It was after Stockton, but before Gonzaga basketball got really big. So studying electrical engineering there, and I graduated and started working for a printer company, designing algorithms to drive the print head faster. And a friend of mine had applied to grad school, and I asked him, what is that? And he goes, oh, you get to keep going to school and study something deeply. And a friend of mine, and I So I just half-heartedly sent off a application to University of Washington grad school. And by the time they accepted me, I had realized that designing printer algorithms isn't what I wanted to do with my life. So I went to the university, had no idea what I was doing, didn't know you needed to, have a lab to work with, or you could teach to help offset your tuition. And I ended up with Les Atlas, who was big in signal processing. He introduced me to the folks over at Microsoft Research, who got me into speech processing. And then I did a few internships there, ended up getting a job there when I graduated, worked there for nearly 20 years, working on advanced speech recognition techniques through the advent of neural networks and end-to-end models and all that, and GPU processing and all that. And about 2.5 years ago, I decided it was time for a change, and I looked for a place to land, and Alexa and Amazon is what I chose. Alexa, stop. Around here, she who must not be named.
Right.
And so I've been working here for 2.5 years, and based on my background, I'm comfortable with everything speech and audio, and so I have my fingers in a lot of stuff. The easiest way to understand it is anything that goes from speech to a structured representation of that speech and back again. That's something that I care deeply about and have my fingers in.
That's excellent. So while yours is significantly longer, you and I have similar paths. I spent 9 of the early years of my career at Microsoft, not working in the research that you were doing, but I spent a lot of my time in whatever the latest and greatest software development technologies were.
Yeah.
And I left there in 2015, just as Alexa was kind of coming online, and jumped over here to join this team. And so it's been no looking back since. This is absolutely incredible technology that I'm so happy that I get an opportunity to work with on a daily basis.
Right. Yeah, even before Alexa came out, people were going to Amazon that I knew, and I was thinking, what the heck is Amazon doing with all these speech scientists and computer scientists, right? And what could they possibly be building? And it was shocking when it came out. I remember some of us in a room with one of the first Echoes, and we put it on the table and we used it, and then we stepped away, and then we started playing music and using it, and it was like, how the heck did they do this? Such a surprising development.
Yeah, I would imagine, especially for the folks like you that are in that industry, that are thinking deeply about a lot of those problems, that had to be like, wait, this just got very real.
It did.
That's great. All right, so you said you've for the last 21 years or so, you've been working in the tech industry, and you've been focused on, as you said, speech recognition, signal processing, that kind of stuff. Over that time, what are the things that had the biggest impact on our progress over the last couple of decades? Are there anything that is there any like advancements that you saw that kind of stood out?
Right. So a lot of people might lead off with machine learning and deep learning and all the advances we have algorithmically, and so on and so on. But I think that the very bedrock, what allowed us to start actually doing science on this, standardized data and evaluations. Starting in the mid to late 90s, the field started operating on standardized data sets. So when you published, people knew exactly what data you're using. They knew exactly what results to get, and you could, over time, do better and better. And without that kind of shared view of the world, it's difficult to make process.
Sure.
But nowadays, when we have things
sorry to interrupt.
Yeah.
Was there a catalyst for that? Like, is that?
Yeah,
that's probably not typical in most research fields.
It was the government. So funding agencies like DARPA and IARPA wanted to be able to score the labs that were competing for grant money. And so they developed these standardized data sets like Switchboard and Call Home that were difficult and related to what the technology they wanted to develop, and then seeded the community with this. And so After the evaluations happened, the field was able to still keep chewing on the same data over time and driving down the error rate. And so that's a really big deal. Having the data available and being able to directly compare. It's kind of a no-brainer now because it's a big thing to have these competitions where you have leaderboards online and everybody's working against the same data, and you publish your code and you can see exactly what they're doing. But back in the dark ages, it wasn't clear that that was the right way to go. People, that's one of the innovations that really enabled speech recognition and then machine learning in general to make leaps forward.
That's awesome. So okay, so we talked a little bit about standardized data. Is there anything else
Yeah.
that's up to you?
So the other big thing, especially for speech recognition, was standardized recipes. When I was working with Dan back in Microsoft, he conceptualized and created this thing called Caldi, which is a toolkit for building speech recognition systems. And before that, most everybody was either using homegrown software or something called HDK, which was very difficult to put together. And people would describe in broad terms how they processed the standard data. And then you had to take their prose and convert it into your own software pipeline from these available pieces. And no one is ever quite sure whether you got things exactly the same, whether you're comparing apples to apples. But Caldi, what it did was it created a modern framework, C++ framework, which was great and tooling. But then it also shipped with standard recipes. So you could have a turnkey switchboard system and know exactly how it performed and how it worked. And so now when people publish, they could say, I use Caldi recipe 4B for switchboard. And instead of the prose, people would know exactly what that was. And that also started to allow us to use science and iterate on each other's work because there was more visibility into exactly what we were doing. And so those are the two pillars that over time are very general things. The sharing of evaluations and the sharing of the recipes, I think, were big needle movers.
And did Caldi come out of a specific project or group also, or is that?
That's a good question. So Caldi started at Microsoft Research, and it was a passion project of his. And he spent, I don't know, maybe a year at Microsoft working at it, and then decided that he would be better served if he went to Hopkins, Johns Hopkins University, and continued his work there. And so it got open sourced, and then most of the goodness of that came from his work at Johns Hopkins, and that's true of a lot of the individual threads of things that made the field better. They were passion projects of individuals. It was something that they believed in. They believed that the field needed, and rather than going out and saying, to their manager, what do you want me to do? What do you need? It was more of trying to find out where's the best place that I can be to execute on my vision.
That's awesome.
And then of course, there's the other thing that really helped the field was deep learning. About 10 years ago, it made the leap from kind of toy systems on a small data set called Timid to a large vocabulary system that showed that neural networks can beat the previous technology. And from there, it was, from DNN hybrid systems to CTC that Graves invented, which was better for recurrent models now. And the recurrent models are better. And then integrating language modeling. And then today, we figured the field as a whole has figured out how to develop an all neural systems that map directly from the audio to the transcribed words that were said. And so, but what really kicked it off was the unlocking of exactly how the neural technology is going to be shoehorned into the acoustic model of the hybrid automatic speech recognition systems.
Got it. So that's one thing that's always very interesting to me. I don't know a ton about the inner workings of how all of these pieces play together, but it is quite interesting to me as you think about all of the pieces that have to play nicely together. You've got deep learning, and obviously those neural networks are doing a lot of the heavy lifting for figuring out what the user said and how all of those things work. But it's not just that, right? I mean, there's so many different bits and pieces that all kind of play together.
Yeah.
The thing that always breaks my head a little bit is to think that I set a thing to a device and it was shot off to the cloud as a recording, and then this whole stack of things happens. It fires it off to some back-end service to determine how it's going to respond, and all of that happens. A full circuit is under a second. That is the mind-blowing piece to me, because it seems like these things are possible if I have an hour to process the data, but to do it in such a tiny amount of time is remarkable.
I agree, and in order to build these assistant services, the software engine, not just the machine learning, but the software engineering is wonderfully complex. And in order to meet the expectations of customers, there is a lot of attention paid to how all these individual pieces interact and work. I mean, just when you ask the device to play music, the device is constantly ready to detect when you want to use it. And the standard way of doing this is called a wake word. And so it depends on your assistant, whether you're saying, okay, Google, hey, Siri, hey, Sam, or, mentioning she who must not be named. The device is constantly ready to detect this. And then once it does, it just sets off this stream of activity. The speech recognizer listens to what you say and converts it into a text form. And then it gets sent to a service that tries to determine, what was your intent? And in this case, I want to play some music, and it processes it and tries to figure out, okay, what kind of music does he want to play? Should I turn a light on? Which album? Is this a song or is this an album? And so there are all these individual pieces interacting in the back end, doing the understanding of what was said. And then once it understands, it has to, invoke the text to speech, which is Alexa's voice. And so oh, good, she didn't hear me. And so you render what you want the device to respond with verbally, and then it needs a different machine learning system needs to convert that into audio. And then she comes back and then she says, I'm playing songs from They Might Be Giants on Amazon Music. And you're like, yeah, that's exactly what I wanted. But
you need a little particle man in your life once in a while, right?
What's that?
You need a little particle man in your life once in a while, right?
Oh, yeah. Yeah, Triangle Man's okay. I don't understand how he ended up in the garbage can, but that's okay. Maybe he just needs a little self-confidence.
We could probably do a full hour on the lyrics of They Might Be Giants, that's for sure.
Yeah. Yeah, so the complexity of the system was great, and that's one of the reasons that I came to Amazon. I really love the customer focus at the company, and the number of customers that they do have, and the complexity is just wonderful. Yeah. We all love solving hard problems. It gives us that rush of endorphin, and so it's a great place to be. So. Yeah, in summary, it's complex, but it's a manageable complexity.
Well, that's good, because it feels like an impossibly complex system, and when you've got millions upon millions of people using it, that just adds layers of complexity, right?
Right.
That's amazing. Well, I want to shift focus just a little bit. First, I want to congratulate you. I heard you had 9 papers accepted at the InterSpeech conference this year. That's got to be some kind of world record.
I doubt it. There's some pretty prolific professors out there.
Sure. But 9 is a lot. And for those that are watching that may not know a lot about InterSpeech, can you share kind of the background on what that event is and why it's important?
Right. So InterSpeech, I think, has been going on for about 18 years now. It replaced 2 older speech conferences that were kind of interleaved with each other on odd and even years. So it's been going on in some form or another for beyond my time as a researcher. And it's the one conference that's dedicated entirely to speech conferencing worldwide, with a worldwide audience. So if you want to know the latest results of, how the different labs are approaching the problems, how they're thinking about it, what kind of results they're getting, or if you want to publish somewhere that has the broadest possible exposure to people who are interested in speech processing in all of its aspects, including the things I care about, but also for communications and coding and noise robustness and enhancement. Interspeech is my first choice of conference to go to.
That's a good endorsement.
Yeah. It doesn't. So I'm gonna mediate that with. It doesn't have the gravitas of some of the more premier machine learning conferences where you'll also see speech papers.
Sure.
But for the breadth of the audience and the depth of the content, it's really tough to beat.
That's interesting. I can draw a parallel to that. So I spend most of my time talking to software developers that build for Alexa, and there are two distinctly different types of events that I go to. There are software development conferences where people are coming to talk about anything related to software development. And then there are voice-specific conferences. And these are ones that you're going to find all of the content related to Amazon Alexa and Google and Bixby and all the other services are there. And people are there talking about their experiences and their knowledge and their approach. And it sounds like this kind of fits that same model where Interspeech is very, very focused on just the speech aspect of the research. Where at some of the other bigger, more, like you said, more notable conferences, those also have a bunch of stuff that isn't related at all, I would imagine.
That's right. Yeah. That's right. But then, you do get a nice cross-pollination. I would be deficient as a scientist and researcher if I only looked at my vertical.
Agreed.
There's a lot of great ideas out there that can be transplanted. And science is a fundamentally social endeavor. Probably software also has a big component of social.
Very much.
But if you don't write down what you've done, you haven't really closed the loop. If you don't communicate it, if you don't participate in that global conversation, then you're doing yourself and the world a big disservice. And that's why I really believe.
There's a famous saying, "Steal like an artist," but I've often co-opted that to use like steal like a software developer, and I would imagine that probably works for your stuff as well. It's not necessarily theft, but it's co-opting an idea that you saw in some other research and said, you know what, that might actually work for the things that we're trying to do.
That's right. That's right.
I think that's the beauty of the scientific community, is that there is a lot of knowledge sharing. It's while there certainly are times I see that people try to keep things close to the vest for whatever business purpose. In many cases, it's a very open sharing community, which is awesome.
It is. And if you go down the other road, you go, the movie trope of the mad scientist. They never publish,
right?
And it's a bad road to go down. I don't want to do
that. Was there any key theme that kind of emerged from this year's event?
Well, so like in previous years, there's a lot of work. The majority, the bulk of it, is all about the small changes that makes a positive improvement the way we use our modeling. So this year, transformer-based models were really popular. So there was a lot of work about how to apply different objective functions, how it works on different data, how to different kinds of conditioning, different structures. There's also usually a few threads that are kind of, oh, wow, that's interesting. This has the potential to drastically change the way we're doing things. So a few years ago, that was something called RNN transducer, RNNT, and the listen and spell architectures, which was the first, attempts at creating a unified neural architecture to bring all of speech recognition end to end under one trainable harness. Recently, I think that that thread for me is representation learning and unsupervised training. The researchers have at the major labs have been making really big strides in trying to teach our models to learn about the way we communicate with audio, but do it the same way humans do, where we're not giving it explicit training signals. It's just observing and learning about our speech patterns. And that has a lot of potential for the goals that we have as an organization.
All right. So I know one of the papers you have is called Scaling Laws for Acoustic Models.
Yeah.
And I would imagine, as with any kind of software, there are perceived limits to how things can be done, right? Unreasonable limits on the size of data or models.
Right.
Can you tell us more about that specific work?
Yeah, sure. If for people who've been paying attention to machine learning in the last, or deep learning in the last 2 or 3 years, there has been a real excitement in text processing around building bigger and bigger models on lots and lots of data. And so there's companies now creating models that are orders of magnitude bigger than anything we would have considered reasonable before this arms race started. But the thing that interests me is that before a person builds these very large models, we don't know how to properly choose the model size for our data. Like, is it that just bigger is always better, or is there some diminishing returns? We don't know, once we choose a size of the model, how much data are we going to need to train it with? We're kind of blind to that. Mm-hmm. And so I believe the default path is just to experiment and, try and throw more parameters and more data and see what happens. But I want to enable a more systematic approach. And with this work, I've demonstrated that it's possible to experiment with some small models and small data and accurately predict how the bigger models are going to behave. So you can make more intelligent choices. Like if you were to characterize your task in data, you can use this framework to predict what is the performance of a model that's unconstrained by data or parameter count. Like, what is the fundamental limit of this model architecture on this data? How well can it do? And that's an interesting question to answer without actually, or get a peek at, without actually, doing the effort of creating the large model.
Yeah, I would imagine it takes a while to construct and run, significantly larger size models. So that this is ultimately a research time saver at the end of the day.
It is. Yeah, and so you can imagine reasons why I would want this more methodical approach to doing it, is because it does potentially speeds up experimentation and gives you some visibility into your hyperparameter space. There's a couple of interesting things to me that also fell out of this. In addition to being able to cheaply design more efficient and more performant training hyperparameters, you can also use this as kind of a language to compare different model architectures. So in our field right now, there's a type of model called a transformer, and there's a type of model called an LSTM. And people will publish a paper and say the transformer is better, or they'll publish a paper and say the LSTM is better. But you can use this kind of characterization of how does the model behave as the data and parameters are scaling to say things like, LSTMs are more efficient for small footprint, and transformers are more efficient for large footprint, and really tease that apart. So you're no longer talking in absolutes, but you're making a more reasoned argument about what's the right tool for the job.
Yeah, I think that makes sense. About it. So I'm about to read something from the page because I want to make sure I get this right. But what I'm going to ask you to do after I do this, we're getting on to your next paper, is I'd love for you to explain this in kind of layperson's terms to our audience, because I think what I'm reading sounds very interesting, but I want to make sure that they understand it. So your paper proposes that an attention-based deep learning model automatically derives optimal syllable level representation from frame level and phoneme level audio features. Now, we spent a decent amount of time here talking about phonemes and syllables and how a lot of those pieces fit together on the software development side. But I'd love to understand the significance of this work and kind of what that really means to a user or a software developer.
So this work here was really driven by my colleague Daniel Kosekwa, and he has a real passion for trying to get our machine learning models to work with customers who have atypical speech. So that might be non-native, stuttered, dysarthric. And so he's been using his position as a scientist in Alexa TTS to pursue this passion.
I love that. It's interesting. Of all the software or hardware I've ever worked on in my career, Alexa, well, Echo has such an opportunity, and really has taken advantage of a lot of it, but an opportunity to really address accessibility head on. The ways that they think about, vision impaired users using the device. They just introduced a keyboard mode inside the app so that people that don't have a voice or can't speak well can type to the device instead and still get all the interactivity and things. I think it's amazing. So it's great to hear that our scientists are thinking about this too.
Oh, right. Yeah. Scientists are thinking about it. And there's lots of great projects bubbling around, what are the simple things we can do? And we have, simple mitigations for stuttered speech. We have for some class of customers, they really prefer to have Alexa speak faster, and we can do that for them. There's some really low-hanging fruit that are real needle movers for the people who use these devices. I'm really proud of the amount of things I see inside the company to address these less typical customers. And so this is something Daniel's been pushing. So I'll talk about it as if it, I might say me or my, but this is really his passion project. And so one of the things that you can do with a computer is you can learn it. You can use it to learn another language, but speech recognition system isn't sufficient to tell you when you're pronouncing things wrong. There's a scene from a classic Mike Myers movie, A View to the Top, where his fellow stewardess is reading off a card, and she's supposed to next assess the window, but she puts the wrong stress on the word assess. She puts stress on the first syllable.
Sure.
And says something entirely different. And so Mike says, you put the emphasis on the wrong syllable. And so the speech recognizer would write down the correct word, but you would have no concept that you said it incorrectly. And I'll leave it up as an exercise to the audience to figure out what exactly the steward said. So the key of this work was beforehand, there was a very manual and brutal way of automatically determining the stress pattern that a person uses when they're speaking. And so the thing that Daniel did here was look and see what are the big guns we can pull out here in order to better assess the stress pattern that a person is using. And so he brought in the attention model, which is a type of machine learning structure that helps you identify where in the audio you need to pay attention to solve your problem. And he brought in some synthetic data where he causes the TTS system to say things wrong. And uses that as extra training data because, of course, data for people pronouncing things wrong is quite sparse, and ended up getting a really great result. You asked about the implication to the developers. So this type of component is most likely going to be it's most likely to be used in a system for second language learning. Where a person's improving what they're saying. But it can also be used in potentially in an assistant software stack, where automatically it's understanding that this person is a second language learner and is maybe saying things wrong and makes it more lenient somehow. I don't know exactly how that would work, but it's possible. But in terms of the people developing the skills for the assistant, it would be, just perceived as a higher success rate among the customers.
It raises the question too. You said that the speech recognition system understands the word even if they use the wrong emphasis.
Yes.
But they're not saying it correctly. And it's interesting to me to think then, if it can understand them, is it incorrect? Because clearly it is managing and appropriating the word properly. But I certainly understand what you mean, though. Like if you and I were to speak and I kept saying emphasis, you would be like, no, we need to fix that.
Well, there's lots of dialects in the and different ways of speaking, even within the contiguous United States, and assistants that are serving that population need to be robust to all the different ways that people talk.
Yeah,
it's just much easier if you're able to either make the system aware of the the scope of things that people might say, the variety of things, or to naturally try and bring that down by using more. I want to avoid the word standard, but a more popular way of speaking.
Okay. One of the other things that you're working on is the application of large data and general machine learning algorithms. And it sounds like a lot of these were previously kind of hand-authored speech recognition components, which I can't even imagine the effort required to hand-author a lot of that stuff rather than leaning on some of the rich machine learning we have today. But I'd love for you to give us maybe a little historical view on how things have changed since those hand-authored components.
Right. So a few years into my career, let's say 2002 or so, the constituent components of the speech recognition system were a front end that generates features from the audio, an acoustic model that tries to represent, tries to classify each 10 milliseconds of incoming audio as one of the known speech sounds.
Wow.
And then an HMM that would try and string these sounds together on the order of maybe 50 milliseconds into phones, like this would be about like 43 different sounds in English. And then a system that was hand-authored by linguists that maps, it's like a pronunciation mapping of all the words the system knows from the lexical form into a sequence of phones. And then another system called language model on top of that tries to describe how the words get mapped together into sentences. And so there was this big stack. The front end was hand-authored, the phone set was hand-authored, the lexicon, the pronunciation dictionary was hand-authored, and people were working on these individual systems trying to make them better. And so people you'd specialize in front end. That one of my first specialties was in front end, trying to produce acoustic features that weren't affected by background noise. Or you'd specialize in language model, or you'd specialize in clustering the sounds together. And so it was just this very big box full of components, and each one was associated with a black art that you had to be inducted into in order to understand what it was and how to improve it. And, about 10 years ago, again, when we figured out as a field, I think it was Saida and you who did the first real big paper on this, was they figured out how the acoustic model could be a deep learning system, could be a neural network. And that was kind of like the foot in the door, because now that you have a neural network, we can start to train things end to end. And so the next step was, we, instead of mapping to these cnones, which are the small pieces of audio labels, and then to phones, can we just map to a sequence of phones directly rather than looking at little slices of time and trying to label it? Can we look at a long piece of time and say, these are the labels in sequence for that? Then that was Alex Graves. He invented CTC, which was a big leap forward there. And so now we have, the HMM and the acoustic model is in the bit in the mix, and then we move to recurrent models here, and then the front end gets subsumed when with the wave to vec paper, where now instead of having a front end that extracts features, we make the end-to-end model aware of the audio itself, the individual samples of the audio.
Right.
And then with the RNNT and the listen, intend, and spell systems, we move even further out and we subsume the lexicon and the language model into this end-to-end model. And so now if you're training an RNNT or a listen, intend, and spell model, there's this machine learning framework inside that's entirely differentiable, entirely trainable. And you just tell it, when you hear this, write down this transcription. When you hear this, write down this transcription. And you give it a lot of paired data, and it just learns what it needs to do. And there's no more linguists coming up with a pronunciation lexicon.
Right.
There's no more idea of clustering audio. It's just audio in, text out, which is much simpler in a way, but we also give up a lot in terms of configurability.
Sure.
And now we have this single black box that's doing the work for us.
Yeah. Now you're relying on the box to be correct on its own, rather than relying on rules and guidance that you've given it specifically. That's that's interesting.
Big trade-off.
Man, that's a lot to take, because that sounds like it probably dramatically affected people's careers too, right? You had to kind of transition. I was one of those black wizards that really understood the front end really well. Now I've got to kind of pivot because that's not as important anymore.
That's right. So I think that this isn't true of machine learning or speech processing, and specifically this is true, I think, for the majority of careers you might take, that being agile and moving with the wave is a great strategy. And so in my career, I moved from front end to, I actually took the path of the audio through the speech recognition system. I started out working on front end, and then I went all the way through to working on the decoder and the language modeling. And now I'm doing end-to-end systems. So I've been a wizard all the way through. As the different pieces got consumed, the scope of what I was working on changed. But yeah, go ahead.
No, it's okay. I was going to continue on here. I have a follow-up question to that, which is, do you imagine a world, and I'm going to ask you some questions about the future coming up here in just a second, but do you imagine a world where there is just the speech recognition system? Or do you think that there will always be a world in which there are individual competing efforts at this? Or do you think that we will ever get to a point where it's just like, we should all just use this one?
I generally try not to predict the future, especially in a recorded medium, where they can come back and see how right or wrong you were. But
you're welcome to pass the question too, if you.
I'm happy to address part of it. I think that I'm going to make an analogy to the early days of computing, where not everybody could own a computer because it was so expensive and so unweighty. And today in machine learning, labs like OpenAI are able to train, trillion parameter models for language modeling. And I don't think it's the right solution today for everybody who needs a trillion model parameter to go out and train one necessarily.
Sure.
There's probably a lot of people who could be well served by borrowing someone else's. And so so in my mind, it's a real trade-off between, how much effort is there to build the thing, and what is the goodness of sharing what was built versus creating a solution for yourself. And over time, I think that the variables that lead into that decision are going to be shifting. And we're going to make different decisions about whether everybody should be using the same model, or everybody should be using specific models, or it makes sense to distribute, or it makes sense to centralize. In computing, where the computing happened has been shifting over the past 40 years. And I think that same thing's going to happen with machine learning.
Interesting. All right. Sorry, I didn't mean to throw you that curveball. I just felt like that was an interesting thing to think about, that we could all just end up unifying on.
Great question.
On a model. So, okay. So I do want to talk to you a little bit about the future, though. I mean, you've been in this industry for over 2 decades. What is the things that I'm not calling them predictions, but as you look forward, there are things that you're like, man, I think we're actually going to we might be able to accomplish that in the next 10 years. Are there things that stand out to you over the next decade? I know one that probably isn't on your list. Everybody that I've talked to about this kind of agrees that sarcasm is really hard. And so I won't hold you to talk.
Oh, yeah, right.
I won't hold you to talking about that topic, but are there other things that you see that are like, I think we may have some success with this?
So up until now, or by now I mean plus or minus 2 years, the speech recognition has been about writing down what a person said. And the inherent assumption here is that the written form contains all the information we need. But that's not necessarily true. My favorite example is the phrase, "I love dogs." If I just say it in a neutral tone, it's it's a fact, you can pick it up. If I say, "I love dogs," then it's understood that I'm trying to emphasize that it's me doing the action. If I say, "I love dogs," I want you to pay attention to the feelings I have for the dog. And if I say, "I love dogs," then you can understand how I feel about dogs versus other household pets. And so there's this meta information that we're not getting by just writing down what was said. And so in the concept of a personal assistant, I might ask to hear Californication, and it says shuffling songs on the album Californication. I can say, "No, play the Californication song," and then that's a strong corrective signal to the device that it was about what exactly the error it was made.
Right.
And that's different from play the Californication song, which is an indication that maybe they played the wrong song or the wrong album.
Yeah.
So that kind of meta information is getting more into the mind and the intent of the person doing the talking. And maybe that is the first step to solving sarcasm too. But we use speech as humans as a way to have a meeting of the minds and understand each other, and have these mirror neurons firing and understanding and getting in conversation. But that's really missing from the way we're interacting with computers, because the only thing, if it's a straight up speech recognition system, the only thing it knows about is the text of the words that you said.
Right.
And so that's what I think would be a great advance in the next decade.
I like that, though. I mean, that "I love dog" sentence is so simple and concise, but it really does have so many different meanings based entirely on how you say it, not what you say. That's a great example. All right, so we are wrapping up here. We only have a few minutes left. One of the things that I'd love for you to offer any kind of guidance you have to people that are thinking about getting into a research career, specifically at Amazon. Do you have any guidance or advice you can offer to folks?
Yeah, I'd be happy to. So I'm going to share some things from my experience. I'm not telling people exactly what to do with their lives. This has just been things that are generally true for me. A general piece of career advice I give to people when they ask is be open to opportunity. It's natural once you start down a path to continue to follow it. And that's really good because it causes you to think about your problem space more deeply. It allows you to develop better solutions over time. And this is exactly what a master's or a PhD program does for you. It allows you to think deeply about a problem, undistracted for a few years. But it's really important to balance that with stepping back and looking around to see, is there something else you should be doing? Is there an opportunity here that I'm missing? And I personally, if I stayed on track in my career, I would still be developing algorithms for printheads in Spokane, Washington. I would have missed the opportunity to go to graduate school. The opportunity with Microsoft Research was a diversion, an opportunity that I grabbed up. The opportunity to join Amazon was another one where I stepped back. My computer broke, and I was on vacation in Hawaii, so I was literally unable to log in for 2 weeks. And I thought about it, and I'm like, you know what? I step back, look, and see. It's time for a change. And it allows you to execute on projects that aren't directly in your line of sight. So that balance, I think, is really important, specifically for speech recognition, signal processing. And I guess this applies to all of machine learning. Look for an important problem that no one's solved. Can we make machines learn language the way that humans do? Can we tie the speech recognition and speech understanding more closely together? Or more broadly, if you can find something that the entire field is currently overlooking, that's super impactful. Some assumption we're making that needs to be changed, some new way of doing things, that is a recipe for success. And that's what Dan Povey did when he created the CALDI system. And specifically to Amazon, come to Amazon if you're passionate about customer-obsessed science. Amazon strives, they say this all the time internally, to be the world's most customer-obsessed company on the planet. Everything that Amazon does is in service of the customer. And the science that we do as applied scientists shares that sentiment. The company is happy to invest in long-term projects, short-term projects, risk-adverse projects. But there's one thing they all have in common, is that when we start out, we know what success looks like, and success is making something better for our customers. And so that really speaks to me. I was trained as an engineer, as an undergrad, and I still have that engineering mindset. I want to build things, and I build things because I want to build things for people. Right. And I found Amazon to be a great place to do that.
I agree. I think that there's nothing more refreshing than being able to sit in any meeting and have the defensible position to be able to say, I'm doing this because of our customers. I'm doing this to solve this problem for our customers. You can say it's too expensive or too hard or whatever, and that's fine. But at the end of the day, this is something that we need to do in the best interest of our customers. And that's an incredibly strong position to hide behind with anything at Amazon.
Yes, absolutely. Absolutely.
All right. Well, Jasha, I want to thank you so much for being here today. You have taught me plenty about some of the inner workings of our systems and certainly some of the research that's gone into a lot of those things. So I want to first thank you so much for being here today. For our audience, I want to make sure that you guys have an opportunity to check out Amazon.science. If you haven't been there, you can find lots of published papers, including several from Jasha. And I would also encourage you guys to check out the InterSpeech 2021 conference, where, as we mentioned, Jasha is going to be presenting 9 different papers. So it should give you a flavor for kind of the work we do here, especially on the Alexa AI team. And you can always go to Amazon.science to see the latest research techniques and YouTube videos and all sorts of cool stuff there. So Jasha, again, thank you so much for being here. I'm going to end us with showing a quick video that's talking about meeting the scientists that work at Amazon and Alexa. So we'll sign off here. Thanks so much for being here.
Jeff, it's been a pleasure. Thank you for the conversation. I really enjoyed it, and thanks for everybody for watching. It's been great to talk today. Thank you.
Thank you, everybody, for tuning in. We'll see you next time.
My name is Olabanji Shonibare. I am an applied scientist at Amazon. I work with the Pro Language Understanding Service and Response team within Alexa Speech.
My name is Aparna, and I'm a senior applied scientist in the Alexa speech recognition team. Currently, I'm working on building better experiences for bilingual customers of Alexa, just like myself.
My name is Venki. I'm an applied science manager in Alexa AI. Me and my team of scientists work on different paralinguistic signals associated with voice. As we know, Alexa is used by many customers across languages, across age groups, with different types of voices. We make sure we understand everyone irrespective of their variance in their voice.
Hey there, I'm Jaime Lorenzo. I'm an applied science manager in the Alexa text-to-speech research team. I joined the team 3 years ago with a task to improve the expressivity and naturalness of our synthetic voices. and this resulted in the release of the emotional capabilities for Alexa. Currently, I am working with many other teams trying to push forward the envelope of what we can do with our technology.
I'm Kayoko. I'm a senior speech scientist in the text-to-speech team at Amazon. I joined Amazon 5 years ago and initially worked on the launch of Amazon's first Japanese text-to-speech voice in the Polly service, followed by the launch of the Japanese Alexa. And more recently, I've worked on the launch of bilingual Alexa, making the American English Alexa voice speak Spanish.
Buenos días, mi gente.
I get to work on problems that are not well defined. You will be expected to develop and deliver end-to-end solutions. You would work on problems that are unstructured. And then, depending on the level, you might be expected to mentor a junior colleague as well.
One of the things that anyone will notice when they work in Alexa AI is the amazing group of scientists and engineers that we have around here. So there's lots to learn. Over the last 2 years, I've learned quite a bit. It's helped me become a better scientist, a better thinker, and a better employee.
We are constantly learning new things, so we are having to adapt and adopt new technologies. Not only that, we are keeping learning, we are keeping absorbing technologies from other fields such as NLP or computer vision. There is always a chance to keep learning new things, so I'm never bored.
Many of the problems that I worked on did not have any prior research work on it or very little of it. There are also problems on which there's plenty of research available, but many a times the work done on academic data sets doesn't really translate when we work on solving these problems for Alexa customers. I really enjoy the challenge of working on and solving these problems, and this is really what makes innovation at the heart of what we do at Alexa.
Nowadays, more and more machine learning techniques are being applied across different domains, and in text-to-speech, we're using a lot of approaches developed outside of the speech domain, which means that we see a lot of researchers with completely different backgrounds joining us in TTS.
The customers, they are placed at the forefront of every decision we make. And so if there's any character or skill you think that would enable you to be customer obsessed, that's a plus one.
Alexa is a fantastic place for anyone who wants to work on solving real-world practical problems with deep learning in the speech and natural language understanding space. There's plenty of opportunity to innovate and build state-of-the-art solutions for some of these problems.